of division, the matrices, right? Because if you take a matrix and you multiply it by its inverse, right, you end up with the identity matrix, right? So it's the same thing as saying, take a number, divide it by that same number, you end up with 1, right? 3 divided by 3 is 1. A matrix multiplied by its inverse, you end up with 1, or the equivalent of 1, which is the identity matrix. Right? So you can think of multiplying by the inverse is the same. Is analogous to dividing by that matrix. Right? That's why it's very important. Very, very important thing. If you want to try and solve for something, you're going to have to multiply it by an inverse at some level, usually. Whoa. Okay. Right. So you can't divide by a matrix. Instead, you multiply by the inverse of it. Lots of ways of finding out the inverse. For a 2 by 2, you can actually solve it very simply, right? It is simply, well, what do? You flip over the diagonals, or one diagonal, you make the other diagonal have the reverse sign, and you divide everything by the determinant. I don't expect you to memorize that. Nobody needs to memorize it. Right? So that's all. For a 2 by 2 matrix, this is easily calculated. And if you're into linear algebra, most of you engineers would have worked out ways of calculating the inverse of a matrix quite a few times, right? Using various processes of elimination, right? So some of that might have stuck. But the main thing is you end up with a matrix. The computer does all this for you nowadays, right? Nobody ever calculates the inverse of a matrix by hand. The important thing is to know whether or not a matrix can be inverted or not. Right? So let me take a step back again. How do you do it by hand? Well, one way is to calculate the determinant, right? Remember what the determinant is? That times that minus that times that, right? That's the determinant. Then you reverse the signs of these guys, of the off diagonals, right? And you flip over these guys, right? And then you divide everything by that determinant, and that's your inverse, right? So your matrix, then multiplied by the inverse of that, will give us the identity. Okay, but that's not really that important as far as I'm concerned. I don't expect you to be able to calculate the determinant by hand, or the inverse of a matrix by hand for any exam. I might ask you to do it for an assignment because I'm an asshole, but really, it's not going to be hard, right? I mean, if I ask you to do it in an assignment, just get the computer to do it to double check your answer, right? That's a smart thing to do. But you'll have to show how to do it, obviously. Right, so why is the determinant important? Because if it's 0, then you cannot calculate the inverse. And the inverse of a matrix is really important. A matrix without an inverse is known as a singular matrix. Right? If you have, for example, a covariance matrix with lots of variables that are all perfectly correlated with one another, then you have a lot less data than you think. Right? You think you might have 10 variables, but actually, if they're all perfectly correlated, there's only one variable of information there, worth of information. And you end up with a matrix that is singular. Right? What happens is, essentially, the rank of the matrix, the amount of information is much less than what you think it is. Right? There are certain coding schemes for variables, design variables or factor variables, that can cause singularity as well, causing problems. Typically, you get a singular matrix if you have too little data and too many variables relative to the amount of data that you've got. Okay, that's the most common. If you've got a lot more variables than you do data points, or even just any amount more variables than data points, then you've got more problems. You've got lots of problems. You can't typically invert that sort of matrix or the model of that matrix. If your data matrix is singular, right, you can calculate the inverse of x transpose x, right? That basically leads to something called the generalized inverse. You're doing what is equivalent to something called a singular value decomposition, which can work with all sorts of different types of data and is very useful, but I will not teach you in this course. right? But do be aware that SAS will use this often to calculate an inverse where you don't have enough data. Right? Okay, so what's the take-home message? A singular matrix, one where you cannot calculate the inverse, is not a good thing. It's a problem. Okay? Geometrically, what are we talking about here? Let's see if I can give some context to what that means. Right? There is no inverse to a matrix A if I can find a vector which satisfies the equation A times X equals 0. Right? Now consider this matrix here, 1, 2, 3, 6. 1, 2, 3, 6. Is there a vector that you can get which, if you multiply that matrix by that vector, will lead to 0, 0? What is it? Think of it, yeah.
We can find the determinant of it and we can equate it to 0.
You can find the determinant is equal to 0. Well, that's a good point, isn't it? What is the determinant of this matrix? 1 times 6 minus 3 times 2. 0, right? So you're right. We know there's a problem. But let's answer the question. Is there a vector? If I multiply that vector by A, that will give us 0, 0. Any ideas? No? Well, what have we got here? We've got this, basically, this is 3 times that, don't we? So if we got minus 3 times 1, something like this, minus 3, or 3 times minus 1, 3 times the first and minus 1 lot of that, that will give us the 0, 0 vector, right? So that's another, so we can see, essentially, what's the problem? We have a linear combination. The second column is a linear combination of the first column. Right? So that was a good point about the determinant, right? You could see that immediately. So why does that lead to problems? Well, you can't invert this sort of matrix, basically. You can see it leads actually to a logical problem. Let's say we have the matrix, suppose you multiply the matrix AX again by its inverse, A inverse, right? So we know that A times X times the inverse of A, that should equal X, right? Because A times the inverse of A is equal to the identity. So you should just be left with X. But if A times X we can find is equal to 0, then it doesn't matter if we're multiplying by the identity, we end up with 0. So we've got this situation where it's equal to both. It can't be equal to both X and 0, right? We know X is not 0 in some cases. So in these situations, we have a vector which takes us into this 0 space, which we can't geometrically recover from. We can't, if we got everything else, if we have a vector that can take everything down to 0, 0, 0, we can't escape from that, right? We lose all the information. So I'll try and show you this geometrically. So we're saying the matrix A is not invertible, right? If you can find a non-trivial solution to the problem A times X equals 0. Right? So geometrically, this is stating that we cannot combine the vectors within our matrix and reach any point in the space. So consider this matrix here. 1, 0, 2, 2, 1, 0, 1, 3, 1. And I'm asking you, is there a solution to that? Right? I don't expect you to answer this question right now. We can consider this matrix 1, 0, 2, 2, 1, 0, 1, 3, 1 as 3 vectors, right? These 3 vectors are sitting in 3-dimensional space. So here's the first vector here, the yellow vector. 1, 0, 2. There's the next vector is in red, pointing in this direction. It's 2, 1, 0, and there's a third one in 3-dimensional space, 1, 3, 1. Right? I can combine these vectors to reach any point in this dimensional space except 0, 0, 0. Right? There's no combination of these vectors that will give me 0, 0, 0, except for the trivial solution 0 of 1 plus 0 of the second plus 0 of the third, right? I will exclude that trivial solution. But there's no non-trivial way of combining these vectors to get to 0. alternatively, I can reach anywhere in this space. I can combine these vectors and reach everywhere else in this three-dimensional space, apart from that 0, 0, 0 point, right, in any way. Right, now let's have a look at this matrix here. 1, 2, 2, 2, 4, 4, 1, 3, 1. Right? We can visualize these three vectors lying in your three-dimensional space. Right, so here's the yellow vector, here's the red vector, and we note that it's lying in exactly the same direction, it's just longer. Right? This is 1, 2, 2, this is twice as long, it goes 2, 4, 4. But it's in the same coordinate direction, right? And then we've got another one that sits that should be in black, right? 1, 3, 1 over here. Those three vectors are actually sitting on a plane, aren't they? Because two of them are actually sitting in the same space, same direction. So these three vectors are sitting in a plane. I can't get off that plane, right? No matter how I combine them. There is nothing in this direction in those vectors that'll take me away off that plane. I can combine them some way. I can say, hey, 3 of the first and 2 of the second, right? Lie anywhere on that plane, I can combine it without using 0, so in fact hit the 0 point if I want to. But I cannot get off that plane. What these vectors are doing, in fact, is just defining a subspace, a two-dimensional. They only define a two-dimensional subspace. They're not. This matrix is not a full rank. It's not a three-dimensional data set. Really, all the information lies in 2 dimensions. Okay. Does that make sense? So this is when we have problems, essentially. When you can see it now that the variables are correlated with one another. That's going to cause problems. Why is it causing problems? Well, it means that you're thinking you have lots of information, but actually these variables are pretty much telling you the same sort of thing. Okay? So, what have I just shown you? That if a column of a matrix is simply a scalar of another column, then that matrix will be singular. You cannot invert it. Right? And we've already done this. Thanks to Arco, he said, hey, look, let's look back to this matrix here with respect to the determinant. Right? 1, 6, 2, 3, the determinant is 0. Right? So if we're thinking about this data set, if we have data that lie on this plane, the volume of that plane is 0 because it's lying on a flat plane, right? It's if the volume described by the data points is spanning the three-dimensional space, then the determinant is not going to be 0. Okay, so I've done that already. We'll talk about these guys again. I just want to talk about covariance matrices. So let's think about this, right? What does a covariance matrix that we're going to be using so often, what does it do to a vector? Right? So I can think of, if I take a vector, let's say each of these data points represents a vector. Right, so this is just white noise data. That's white noise, so it's a random scattering of data points with a standard deviation of 1. Okay, if I multiply it by a covariance matrix like this is the covariance matrix 4.25, 4.29, 3.1, 3.1. Right, what happens to these data points? If I multiply by that, I end up with the structure in my data. So the white noise gets turned into data set with specific structure. It's going to have a variance along this way, a variance along that way, and a covariance, a positive covariance between the two. Right, so you can think of your covariance as acting to basically skew your data, or if your data is basically white noise, it finds the shape. It's describing a shape, a transformation, a particular shape of that. And that shape is dependent on the variability of each variable and also how they covary with one another. Right? That's what the covariance matrix is. It's basically an extension and a rotation.
What is white noise?
Sorry, white noise. I just mean random data points within a 1-1 circle. Yeah.
Oh.
Yeah. So I just mean random data points scattered around the particular points. It's a good question. Sorry, I didn't make that clear.
Where do we get the parameters of this covariance matrix?
This is just a covariance matrix that I made up. You could what would a covariance matrix, let's say, I don't know, think of one, 5, 2, -1, -1, right? What would that look like? Well, x1, x1, x2, x2. So this is saying the variance of x1, the spread of the data would be 5 units long, right? This is saying the spread of the data along x2, the resultant matrix would be sigma squared equal to 2 here, right? So we know that there's that, but also there is a negative relationship between these two guys. So it is going to look something like this. Oops. Probably like that. So you can think of this matrix as being a model of the data.
So I may try multiple matrices to identify the population.
Now, so what I've done is sort of the inverse of what normally we do. Normally what we do is we get a data cloud and we find the covariance matrix that describes it. Right now I'm just saying, well, given any random data points and then we multiply by the covariance matrix, this is what we get, a data cloud. So my point really is just elucidating this idea that the covariance matrix is a model, right? You can think of it as a model that acts on vectors to describe a data cloud that lies in a particular shape, right? And that shape is defined by all those points of the values of the covariance matrix. Okay, so the determinant, what is it? It is the parallelepiped of dimension p. So here we've got a three-dimensional parallelepiped, right? So remember what happened when we only had all of our data were lying on a plane? That volume collapses down to a plane, so it turns into 0, right? The volume of your parallelepiped is maximized when all your axes, so if you're going from here and it's going to be, as you rotate, let's say this box, you're sort of collapsing it down, right? So on a flat line, the volume is 0. As you start rotating it, the volume gets bigger and bigger, right? Until eventually it'll be maximal when you've got a nice cube. That's the biggest volume you can get, right? That's saying when the axes are mutually perpendicular, right? That means when the axes, another way of saying that is the axes are orthogonal. Right? When I choose the term orthogonal, the best thing to do is just think of the term, they all lie at right angles to one another. All the axes are lying at right angles to one another. Okay, and we're going to do this a great deal. We're going to find a data cloud, and then we're going to find a new set of axes that go through that data cloud. And the axes are going to be orthogonal to one another. They're going to lie at right angles to one another. Right? And I'll show you what I mean in tomorrow by that, why that's important. So, what we typically have to do is transform the data in some way. So it's very useful to find an orthogonal basis to work with. Right? So what we have is, the data lying in a cloud, right? But that cloud has structure, right? Typically, there are covariances. And so movement along one axis also probably means movement along another variable that's correlated with it. So it's very nice to have axes that are completely at right angles to one another, meaning that if you go along one direction, it has no bearing on what's happening in the other directions on average, right? So let me give you an example. So you have a data cloud like this, right? So all the data points are in this cloud, right? As I increase, this is two variables, x1 and x2. As I increase x1, I'm also affecting what's going to happen with x2. As x1 increases, x2 tends to be getting bigger as well, right? But I can draw a set of orthogonal axes through this data cloud, where as I go across one axis, it's going to make no difference on what happens on average with the other one. Okay, so I'll call this axis 1, and this is axis 2. Right? So we knew, dealing with x1 and x2, as x1 got bigger, x2 on average got bigger as well. Right? there was a correlation between them. With this new axis, axis 1 and axis 2, here, they are orthogonal to one another, they're at right angles, and with respect to the data, as I go along one axis, it doesn't tell me any information about what's happening with axis 2, right? As I get bigger on axis 1, that doesn't mean that the values are getting bigger on average in axis 2. Right? So what I'm trying to do is find a set of, basically, find a set of axes through my data cloud that lie at right angles to one another, right? That is useful in some way, right? And we'll get into that in greater depth. So don't worry too much about this. It'll become clearer in time. Right, so what we're going to do is we're going to try and find an orthogonal basis to work with, right? An orthogonal set of axes, what I mean. Set of axes that are all lying at right angles to one another, right? And we're going to use an eigenvalue decomposition to give this, right? So the eigenvectors are, in fact, that we're going to derive are going to be these axes that go through our data cloud. Right, so the identity matrix is a three-dimensional orthogonal basis representing a unit cube. Right, what does that mean? Well, it sounds very complex, but it's not. All it means is, well, we've got 3 dimensions, that's obvious, so as a consequence, the data lie in 3 dimensions. If there are limits to 0 and 1s, these are the variables, then of course they are, it's going to be a cube. Right? If your data lie in that range between 0 and 1, any data point that you get is going to lie somewhere in this cube, right? And we can define that by, where it is with respect to this variable, and this variable here, right? So we can look at this second data point in the cube as well. In fact, we can do it lots and lots of times, and we can look at all these data points. Hey, look here. Look at this data set. It is populating the cube very nicely, right? Because our cube is uniformly populated, it's actually a good approximation for these 3 variables. But what about this? What happens if we've actually got some kind of data sitting in a plane? This is actually supposed to be hard to see, but the data is actually lying in a plane, right? We don't really have 3-dimensional data. We have 2-dimensional data here, right? So we could actually, if we could try and find a basis, a set of axes that goes through that data, but with only 2 axes, that's going to describe very well what's going on with that data cloud. Right? That's what we want to do. Find a new set of axes, and that's probably going to be a combination of the original ones, right? That is going to describe this data cloud in a better way. So what do we do if we've got lots of dimensions? How are we going to do this? Well, we'll talk about it tomorrow, how we do it. But if you've got lots and lots of variables, let's say we've got 15 variables. How do we work out how many orthogonal dimensions there are, right? How many variables are, what sort of space or subspace can I use to define this? How much can I reduce my data space, in fact, is what it's all about. You can't simply graph your raw data and find this out. If you've got 15-dimensional data, right, how do you know if all your data is sitting on just 3 dimensions of it, right, or 4 or 5? This is one of the things that we're going to learn, right? So what we're going to do is decompose the matrix of data, or the covariance matrix, in fact, and reconstruct the data according to that. And that's going to be what we'll do tomorrow. It's too late in the day to try and do that today. Okay, so that was all I wanted to talk about. It sort of gives a taster of why we're going to do what we're going to do. And it will become clearer by the end of tomorrow why we're doing it. Okay, I understand this is all very abstract, right? It's high-dimensional space, what does that mean, man? I don't know, but it's pretty cool. It's, yeah, it will become clearer, right, when we talk through PCA and eigenvalues. I understand it's pretty abstract right now. Okay, so that were the lectures that I wanted to talk about today. Let's carry on with the Lab 1 and Lab 2.